Welcome to another edition of the Rust Munich Meetup. This is the third this year, the third quarter. Today we have two talks. One is by Sebastian regarding Bluetooth on the Linux desktop, essentially. And the second is about everything is an expression, something a little more sophisticated. Before we go forward and listen to the talks, I want to thank our sponsor that provides us with the equipment that you, dear streaming listeners and tuners, are experiencing, the microphones. So it's TechnoSearch, and well, you here at the menu, you can't see this. TechnoSearch is essentially a headhunting company for Rust people. Yeah, so let's start with our first talk. But before that, Scandio, who provides us the venue, would like to introduce themselves.
Yeah, thank you. My name is Max. I'm from Scandio, and I organized this meeting here today. And before I bring you to my company, I'd like to thank my colleagues who helped me set up everything here and provide you all with pizza and stuff like that. So thanks to them also for cleaning up later. Who are we? Scandio is a company located in Germany. We were founded in 2003 by Christian Koch and Christoph Körbele. We have locations across the country, like in Munich, Augsburg, Berlin, Stuttgart, and Regensburg. And our head count currently is somewhere above 200. Don't know exactly how much it is right now. We are part of the HIQ group, which is a group of other tech companies working together, sharing experiences and stuff like that. And we're also proud to be one of the first Atlassian Platinum solution partners in Southern Germany. Our motto is to digitalize products, processes, and organizations. And how are we doing that? We support the clients across all parts of IT. So from the IT consulting to the development and also to the maintenance in the cloud service area, which covers topics like IoT, web applications, cloud, and also AI. We are currently very eager to drive the AI topic. We have a lot of customers and a few projects already, and are also searching for new projects in regards to AI. How are we working together? We are self-organized. This means we're split into domains and clusters. Domains are, for example, development and the consulting part. And the clusters are then subgroups of these to further split down the teams. We have topics. Since we're self-organized, everyone can join topics or COPs, also called communities of practice, where we can share experience and also learn new things. And this is all self-organized, so you're free to join any topic or COP, and also feel free to leave already if you're not interested anymore. We don't have anyone who's in charge. We have project responsibles, like I am, for example, where it's more like for the organizational part of the teams. And we also have Scrum Masters, of course. And as I said, we're self-organized. We want to have an open community, communication, and we also value transparency a lot in our company. Who are we working for? There are quite a lot of companies. The big ones, BMW, for example, Infineon, ESH, Siemens, and a lot of others. So Rust at Scandio. Since you're here, you're probably interested in Rust. We don't have a project right now with Rust as the main language, unfortunately, but we used it already in some side projects. We snuck it in here and there, made some CLI tools. We have internal workshops. We had some, and we will have some in the future. We participated in the Euro-Rust last year and are also going to participate this year. So we might see us there if you're also joining. And as I said, no projects yet, but maybe in the future. And that's it from me. And I hand it to Sebastian.
Okay, hi. Nice to see you. Nice to meet you. Thanks for letting me talk here. So my name is Sebastian Urban, and a little bit about me. So actually, as you might have noticed, I am not a computer scientist, because only a physicist would try to connect Linux to a projector without preparing at home. So yeah, I did my master's thesis in physics. I did some fluid dynamics and started to do some simulations in MATLAB, which I then tried to accelerate using CUDA. That's how I got into programming. And then I kind of liked it. So I decided to do a PhD, but not in physics anymore, but in computer science. So this was like 7 years ago, when the whole machine learning hype started. So I decided to do a PhD in machine learning and worked with deep neural networks. This was lots of Python, also a bit of F#. This is how I got a bit into functional programming, and also again a bit of CUDA for GPU acceleration. Then when I was finished with my PhD around 2018, I left the academic world and started programming commercially, first in C++. This is writing some code for some mobile RF test equipment and also some 3D image capturing and processing. But then I, by accident, found Rust, noted that it is quite comparable to F#, but on a closer to hardware level, and I liked it a lot. So I started porting some commercial C++ code to Rust, and now 6 years later, I developed like 90% of my time in Rust. During this 5 years, I started 4 Rust open source projects. One of them, which I consider the most important of my open source projects, is VMOC. Maybe I will give a talk about it later, at another time. So it's basically an implementation of Tokyo's channels, the Tokyo library in Rust, which you can also use remotely. So you have the channels MPSC, OneShot, Watch, Broadcast, and so that all work over the network. Then we have BlueR. These are the Bluetooth bindings for Rust that we are going to talk about today. And another 2 projects. One is Aggregator. It's basically a user space implementation of multipath TCP. And another embedded project is OpenEMC. It's a management controller for embedded systems, basically something that you can put on an STM32 and that controls peripherals in an embedded system. So let's get started. So the Linux protocol stack for Bluetooth is called BlueZ. It was started 2001 at Qualcomm and first included in Linux 2.4.6. So it's quite old by now, all implemented in C. And it consists of 2 main parts. One is the kernel code, which is included in the Linux kernel. And it provides device drivers for Bluetooth adapters and Bluetooth middle level protocols. Then there's the Bluetooth daemon, which is a normal user space process, and it manages the high-level Bluetooth protocols and interfaces to normal Linux user space processes using dbus calls. Yeah, I started the BlueR project about 2 years ago. There already were some Bluetooth bindings for Rust. One library was called Blurs. It was quite simple and I needed more functionality. So I forked it with the intention to just add a few functions. But as it is, it became a full rewrite. And now BlueR has become the official Rust binding for BlueZ. So first things first, what do we need? Well, one requirement is Linux. Believe it or not, I have some issues on GitHub why it's not working on macOS. Then you need the running Bluetooth daemon for most functions. You need the dbus headers for compilation because the interface to the Bluetooth daemon is done over dbus. And you need the Tokyo library for the async runtime. Once you have all of these installed, adding the dependencies is very easy. Nowadays, just run cargo add BlueR and specify the feature flag full, so you don't have to worry about missing feature flags. There's also a package called BlueR Tools, which you can install using cargo install. It is completely optional, and we will come to it later. So I kind of started in the middle with Linux and BlueZ and BlueR. Maybe some of you don't know what Bluetooth actually is, so let me quickly explain it. So it was in 1990. There was the need for some short-range wireless communication technology, and it was invented in 1994 by Ericsson, and first commercial use was to connect an IBM ThinkPad to a GSM phone in 1999. So the problem was the modem was way too big to integrate into the computer, but still people wanted to communicate on the road, and cables are not so nice, as you can see. So a new standard was needed for short-range communication. Bluetooth is working in the 2.4 gigahertz ESM frequency band, and there are basically three classes of devices denoted by the maximum transmit power. So it's fairly low power, as you can see, as the highest class. Class 1 has a maximum transmit power of 100 milliwatts and a range of up to 100 meters, but this is very optimistic. In practice, I've seen about like 20 meters maximum. And nowadays, you might already have heard about Bluetooth Low Energy. So what was introduced in 1999 was actually Bluetooth BR80R, which stands for Bluetooth Basic Rate Enhanced Data Rate. This is the classic Bluetooth. There's a data rate of about 1 to 3 megabits per second, and it's mostly connection oriented. So, for example, to connect a modem to a computer or a headset to a computer or two mobile phones together to exchange contacts. And nowadays, the more recent Bluetooth everybody is talking about was introduced with Bluetooth version 4.0 in 2010. It's called Bluetooth Low Energy, and it's optimized for low power consumption and the Internet of Things. So most applications are like connecting sensors like thermometers, medical sensors, smartwatches, and things like that to other devices. And all these devices should be able to run on battery. Some of them should also be able to run on battery without being recharged for a very long time. So a standard was needed to save some power. The most, from the protocol side, the important features of Bluetooth Low Energy compared to classic Bluetooth is that now we also have the ability to broadcast data. So we don't need a connection between two devices to exchange some data. A device can just be sending data to everybody, and all other devices can just receive the data if they're interested. And there's also the generic attribute profile, which kind of standardizes how data is transmitted. So in the Bluetooth specification, there are actually fields and data types defined for all kinds of purposes you could imagine, like heart rate, wind speed, temperature, or also waist circumference. When you have a device, it can also support both the classic Bluetooth and the Bluetooth Low Energy. This is called a dual mode device. So now let's dig a bit deeper into the Bluetooth protocol stack. I heard that people with a computer science background like this OSI model. Actually, I don't know a lot about it, but I just put the picture here to have some comparison for you guys, how Bluetooth layers compare to standard network layers. But what I personally find more interesting is this picture on the right. So on the lowest layer, we have the Bluetooth radio, which is kind of self-explanatory. Then we have the baseband and the link manager. This is all implemented in the Bluetooth controller, which is a chip on your motherboard or in your mobile phone. And when you have a laptop with a Wi-Fi card, it's usually integrated in your Wi-Fi card. So the radio is the physical layer, and the baseband is some kind of digital signal processor, which is implementing the lowest levels of Bluetooth protocols for the over-the-air interface between devices. Then we have this interface between controller and host. The nice thing about it is that it is standardized. It's called the host controller interface, HCI. And that's the good point about it is that you don't need special drivers for different Bluetooth cards, because all of them speak the same protocol to the host. Above that, you have L2CAP, which could be somehow compared to the IP protocol in the internet. It's what's running the first software implemented protocol in the Bluetooth stack. And that's in the Linux world, this is implemented in the Linux kernel. On top of that, you can have various services. For example, if we take this ThinkPad example from 1999, they implemented virtual serial ports on top of L2CAP. And then using this virtual serial ports, they talked AT comments to the GSM modem and also PPP for an internet connection. Of course, you can have all other kinds of services like address book exchange or some special protocol like SDP, which stands for Service Discovery Protocol, to discover the services a device is offering. Then, as you all know, we have this Bluetooth headsets and Bluetooth speakerphones in your cars. So there is some provision for audio, which is also implemented in the kernel, but I'm not going to talk about that today because my focus is more on the data side. So this was the classic Bluetooth protocol stack. The low energy protocol stack is kind of similar. We have again at the bottom, the physical layer, and above that, the link layer, both implemented in the controller. And they are interfaced to the host, again, using the standardized HCI interface. Above that, same as in Bluetooth Classic, we have L2CAP in the Linux kernel. And now to exchange information, we are using the generic attribute profile on top of the attribute protocol. For example, to read values from a thermometer or control some door lock or things like that. And this part, this high-level Bluetooth Low Energy protocol, is implemented in the Bluetooth team. On top of that, you can have your application, which is controlling the data that is exposed via Bluetooth. And we will come to that, how you can implement your own attributes or read attributes from another device. Okay, so quick words about the physical layer, because I'm a physicist, so it's kind of interesting for me. I don't know if it's interesting to you, but it's only one slide, so you can have a short break if it's boring to you. So the classic Bluetooth actually has 79 channels. Each channel is 1 megahertz wide. And Bluetooth Low Energy has only 40 channels, but each channel is 2 megahertz wide. So the reason for using a lower amount of channels for low energy, but a wider frequency range, is that you can save some power in the receiver if you can use wider filters for receiving channels. It's a half duplex radio, so actually only one device can be sending on one channel at a time. But to simulate full duplex communication, so in both directions, you use time division duplex. So in the protocol, it's specified when which device is allowed to send data and when it has to listen. The modulation for the basic Bluetooth radio and Bluetooth Low Energy is Gaussian frequency shift keying. This sounds very fancy, but actually it's the same as FM radio, like the standard radio you have in your car, like Antenne München or Radio Bayern 3 or something like that. So it works like that. If your channel center is at 2402 megahertz and you want to transmit a bit of value 1, you increase your frequency by 185 kilohertz. And if you want to send a 0, you decrease your frequency by at least 185 kilohertz. So if you plot it over the time domain, you see that by sending a 1, the frequency goes up, and for sending a 0, the frequency goes down. This is how you encode your data. For the enhanced data rate, there's another more clever modulation scheme, but I'm not going to go into that right now. Okay, that was the physical layer. So the people with the computer science background can join us again, because now we are going to talk about protocols. So now we are at the bottommost protocol in the Bluetooth stack, which is implemented in the firmware of the Bluetooth controller. So this is the link layer. And as we already said, it's using time division multiplexing to provide first full duplex communication in both directions, and also multiple links over one physical connection. One time slot is 625 microseconds long. And now we are coming to the audio links. We have at most 3 synchronous connection-oriented links, and they all have fixed number of slots in the data stream. So we can be sure that we have a guaranteed amount of bandwidth available for real-time audio. So this is what all the Bluetooth headsets are using. And then the remaining bandwidth is used for one asynchronous connectionless link. It gets the remaining 3 time slots and is being used for data and control information. So this is the protocol channel that is later used for L2 cap, which then again multiplexes this connection into multiple protocols like virtual COM ports, GET services, PPP, and so on. There's always one master device. It's responsible for scheduling and allocation of time slots. And in Bluetooth Classic, we can have multiple slaves, and they can only transmit after they have been addressed by the master device. So if a device has some data to transmit, it has to wait for a packet from the master device, and then it can reply with all the data it is queued for sending to the master device. Also, the link manager layer handles all the encryption and key management in the Bluetooth protocol stack, but we are not going to go into that today. So quickly, this is how a link layer packet looks like. It's not important to understand all the fields. What I want to point out is that basically we have some addressing method, which is encoded in the sync word. We have some sequence numbering. And in the end, we have some checksumming, which is done using CRC. So basically, each Bluetooth connection is an ordered and reliable connection. So of course, it can get terminated if you have some interference, but at least you know that when you receive packets, they all arrive in sequence because you have the sequence number and you don't have any data corruption, at least if you trust CRC32. Now for Bluetooth Low Energy, it's very similar to Bluetooth Classic. Again, we have master and slaves. But now they can agree on some connection interval, which can be quite long. For example, they say we only need to talk to each other every 100 milliseconds. Again, this is a measure to implement some form of power saving. And also the slave is allowed to miss some connection events while it is sleeping to save its own power, which should not lead to an abortion of the connection. But the principle is the same. The connection is always initiated by the master, and the slave can only transmit data immediately after it has received a packet from the master. Again, this is all handled in firmware. We don't have to do anything on the host side to implement this protocol. Again, the packet structure of the Bluetooth Low Energy link layer packets. As we see, again, we have sequence numbering field in the header, and somewhere there is also a checksum. Here it's the start of the header. So also in Bluetooth Low Energy, it's basically an ordered and reliable connection. So if we trust that, we don't have to do error correction on our own. So this was the controller part. And now it starts getting more interesting for us, because now we are coming to the part where we can control this radio. This is done using the host controller interface. As I've stated, it's a standardized protocol. It can use various modes of transport. The oldest one is the serial port, because nowadays it can be a completely virtual serial port, like it's the Raspberry Pi, or it can be over USB, or even other devices use the SPI protocol. USB is mostly used in desktop devices. So if you have a Wi-Fi card, it's usually an M2 card, and this M2 card has multiple pins. Some of them are for PCI Express. This is what's used for the Wi-Fi part. And then you also have USB pins on your M2 connector, and this is what's usually exposing the Bluetooth controller on your Wi-Fi card. So your Wi-Fi card is usually recognized as two separate devices by your operating system. Once for Wi-Fi via PCI Express, and another time via USB as a Bluetooth adapter. Yeah, on the Linux side, we see this host controller interface devices exposed as an HCI device. Usually you only have one card, so you see HCI 0. And you can interface from user space to this HCI device using the Bluetooth management interface, which is a standardized protocol in the Linux kernel for controlling Bluetooth adapters from user space. But usually you don't do this as a user space protocol, a user space process. You have the Bluetooth daemon, Bluetooth key running, and it's usually claiming this device, controlling your Bluetooth adapter via the management interface, and providing Bluetooth services via dbus to all other interested processes. So now let's start. It starts to get a bit more practical. Let's talk about advertising. As I said, in Bluetooth Low Energy, you can just send advertisements over the air to everybody around you, and anyone who is interested can just listen and receive your data. You don't need any connection for that. So advertising is done on the fixed channels 37, 38, and 39. The advertiser just sends data on this channel, and the scanner, the receiver, is just listening on this channel. It's no interrogation or something like that going on. Also, it's a stochastic process. We don't have any guarantee that the sender and the receiver are at the same channel at the same time. So it can take a while until an advertisement is actually received by a scanner. Because everybody is free to advertise on these channels, the amount of advertising data is quite limited. In its basic form, it's only 27 bytes, because it has to fit in one Bluetooth Low Energy packet. But there are also some extensions of the Bluetooth protocol which permit up to 250 bytes. Usually what is fixed in an advertisement is like the Bluetooth address, some flags like what kind of device it is, like a mobile phone or headset or something like that. The device name can be part of the advertising data, and also the transmission power level. This is quite interesting because when the transmitter is advertising the level, like with which power it's sending the signal. Then the receiver can calculate the approximate distance to the transmitter by comparing the received signal strength with the transmitted power level. As I've said, this belongs to the lowest Bluetooth stack, so it's handled by the controller firmware, but on Linux, it's managed by the Bluetooth daemon. So I've talked enough, I think. Let's try some examples. And so you are here to do some, or see some Rust at least. So let's see how we can implement sending advertisements over the air in Rust. So this is actually all you need. You import BlueR in your cargo file and have the usual import statements. Because everything is happening asynchronously, we are using Tokyo to have an asynchronous main function. This is not part of BlueR, but how you would do it when you use Tokyo. And what you first need is to start a Bluetooth session. This is actually establishing the dbus connection to the Bluetooth daemon. You don't have to specify any arguments or such. It's all happening automatically. But if the Bluetooth daemon is not running, it would fail at this point. Then you get the Bluetooth adapter from your system. You could do all the enumeration manually, but let's keep it simple and just use the default adapter in your system, which is usually HCI0. This is what this call is doing. And then, of course, you want to turn it on, otherwise you cannot do much. And yeah, basically this is all what you need to do to have access to the Bluetooth stack of your machine. Now we want to advertise some data, and in the Bluetooth low energy specification, the advertisement data is categorized using UUIDs. So we are creating a map and creating a UUID quite randomly and putting some data into this map that we want to send over the air. Yeah, so we are sending data 1, 2, 3. Yeah. Now that we have that, we put it into an advertisement. And to actually send this, we just call the adapter advertise function. And this will register this advertisement and keep sending it until we drop this handle. Of course, at this point, if the program would exit, the drop function would be called and the handle would be unregistered. So I'm just calling future pending await, which means that it's basically an infinite loop and the program is not exiting until I press Control-C. So this was the sending part. Now we want to also see the process. We run on another device. The start is the same. And now we want to scan for devices, which we can do using the method discover devices with changes. It's returning a stream of events, so an asynchronous stream in Rust. And every time a device changes, you're getting a new event for the device. So then, once we have this event stream, we just have a while loop, which is processing each received event and printing some messages. Then we call the query device method for each device we have discovered. And if the device name matches the name of the advertiser, which is hard-coded in this case, we just print some additional information and also the service data. So this is actually only necessary for the demonstration. Otherwise, I would have way too many devices, way too many noise during the demonstration. So I have two terminals here. One is my local machine on the left, and on the right, we have the Raspberry Pi sitting here. So this is, clear that. This is just a Rust project with some binaries in it, so I don't have to copy and paste the code right now. As you see, here I have the advertisement code, and on my machine, I have the scanning code. Now, I'm running the advertiser on the Raspberry Pi and the scanner on my machine. And it was already discovered. As you see, we have lots of devices here. So here you have it. This is the MAC address of the Raspberry Pi. It was also broadcasting this name. And as you can see here, we have this service data associated with the UUID we have provided. Okay, let's move a bit up in the protocol stack. Now we are coming to the L2CAP protocol. As I told you, it's similar to IP. So advertisements might be useful, but if we want to do some real data exchange for an application over Bluetooth, we ideally would like something like TCP sockets. And we actually can use L2CAP to get something very similar to that. It's a protocol for data stream multiplexing, and like TCP, it provides reliable in-order data transmission, and it also has a concept of ports. In this case, it's called PSM, but it's very similar to a TCP port number. It also does things like breaking down packets and then reassembling them at the receiver if they are too large for the link layer. Also, you have some flow control. So if the receiver is slow to process some data, it can tell the sender that it should stop sending more data to stop some buffers from overrunning. If you are used to doing some network programming with Rust, you know the socket addresses for TCP IP, which usually consist of an address field, which is the IP address and the port number. Here for Bluetooth L2CAP, we also have socket addresses, but they have a different form. They have the Bluetooth physical address, which is 6 bytes long, and then also the protocol service multiplexer, which is a 16-bit number corresponding to the L2CAP protocol number. You also have some other fields like channel identifier and type, but they're usually just set to 0 and only used for special purposes. So let's see if we can create a very simple L2CAP stream server and client in Rust. As I've said in my introduction, L2CAP is actually not implemented in the Bluetooth daemon, but in the Linux kernel. So we can directly do kernel calls from our process and don't need any dbus interface. This is why we don't need any Bluetooth session in this L2CAP client. So what we do is we just create an address for the device we want to connect to. So this is the address of my Raspberry Pi here, hard-coded in the program. And And we specify the protocol service multiplexer, also hard-coded in this case to number 240. Of course, we should also start discovery and wait for the device, but for simplicity, I don't have it here in my example. And then, like with a standard TCP/IP connection, we can just call the connect function. For some reasons, we actually should sleep here because the connection is not very stable in the first 100 milliseconds, which I cannot explain, but it works when you just wait. And then we can just use it as a normal stream using async IO as provided by Tokyo. The server is also quite simple. What we have to do first is we have to start advertising. It's not actually necessary to establish an L2 CAP connection, but without advertisements, the client will not be able to see the server because there is no interrogation protocol in Bluetooth Low Energy. So if the client does not see any advertisement packets with the target Bluetooth address, it cannot find the device. So we are just sending some empty advertisement packets. And then, like in TCP/IP, we create the socket address we want to listen on and create a listener. Then we can use the standard accept call. And once we have the stream connection, we just loop, receive data into a buffer of 256 bytes, and print the received data. Okay, as you can see, this is the incoming connection. Then we have here the message sent by the client. And in the end, the client closed the connection. So as with TCP/IP, we just get a connection reset error at the end. So if you are familiar with network programming, you will be able to just apply all your knowledge to do some connections directly over Bluetooth without the need for any TCP/IP between your devices. So now maybe you want to talk to some smart devices like a thermometer, or smart power switch, or smartwatch. So this is where the standardized GET protocol is coming in. It actually consists of two parts. One lower level protocol, it's called the attribute protocol. It's also running over L2 CAP, over the fixed channel number 4. It's usually used with Bluetooth Low Energy, but you can also use it for Bluetooth Classic devices that implement it. In its basic form, the attribute protocol basically just allows reading, writing, and being notified of changes to attributes. An attribute is a very simple concept. It consists of a 16-bit unique handle, a UUID defining its type, and some value of variable length. So it's basically a hash map that you can read and write to over Bluetooth, and it's standardized. But to make this self-describing, there's also this thing called GET, the generic attribute profile, and it defines how these attributes in this hash map are organized so that they become self-describing. For example, for a very simple thermometer, we have this structure. So for the handle hexadecimal 100, we use a UUID of 2800. So this has a fixed meaning, this UUID. It means that this is the primary service. And the value here is 1816. You can look this up in the Bluetooth Low Energy specification, and it says that this primary service is the thermometer. Then the next handle 101 has a UUID of 2803. It means that what is following is a characteristic. A characteristic is like a value you can read from the device. And by using the value 2A to B, this means that what is following is the actual temperature. Then after this field, we have 102. Now we are coming to the actual value with the UUID 2A to B. And the value in this case decoded is 20 degrees. But this is not enough. The protocol also allows us to specify the unit of the data by using a UUID of 2H1F, and then we can specify the unit in the value, in this case, Celsius. The next handle for the next characteristic has a handle incremented by 10. So this is actually all you see in the protocol. There's no hidden data or something. So the client knows that all this information here belongs together because it has all the digits before the last are the same. Now, the next characteristic would be date time. As you see, the UUID value here is different. 2H00 means time. And then in the following field, you have the actual value, which, for example, is some date and time. So for some demonstration, we implement a simple water heater, which can be controlled over Bluetooth. It consists of a switch, which can turn the heater on and off, and a temperature readout to read the temperature of the water in the heater. So we don't need to implement the GET protocol. This is all handled by the Bluetooth daemon. We just need to talk to the daemon over dbus and tell it which services and characteristics we want to expose. The beginning is as the same as in the previous examples. We start sending some advertisements so that our heater device is actually visible to clients. And then we define a GET application, which consists of a single service, which has the UUID health thermometer. This is all. You could use a custom UUID, but there is actually a UUID for thermometers in the standard. This is the primary service, and it consists of two characteristics. The first characteristic is the temperature, and when this characteristic is read, we want BlueR to call this function here called read temperature, and this function will return a value that should then be sent back to the client that is making the inquiry. All this boxing and so on is required because of the type system of Rust. I'm not going to go into that. And then we have the second characteristic, which is the power switch. I use the value for, I say it's a digital output, and it can be written to. Every time it's written to, we want BlueR to call this function, write heater on, with the value it has received from the client. And these functions are very simple. I use a global static variable to store the status of the heater. In the write function, if the client writes a value which is not equal to 0, the heater is turned on. And if it's 0, it's turned off. And then if the client is inquiring the temperature, we are returning a value of 60 degrees Celsius when the heater is on and 20 degrees Celsius if it's off. The corresponding client is also quite simple. Of course, we first need to discover the device. We have seen how to do this in the Bluetooth scanner. And then if we see that the device we have discovered is actually providing the health thermometer service, we are calling the test device function on it. And this test device function is going over the services of the device, picking the health thermometer service. Then it's going over the characteristics. It's finding the characteristic which is providing the temperature and the heater switch. And then after the characteristics have been found, we first turn the heater off, wait a bit, read out the temperature, then turn it on, and again read the temperature. Yeah, and as you can see, it's quite unspectacular. It found the device, and with the heater off, it was 20 degrees and then 60 degrees. And here we see the debug messages. Yeah, that nearly concludes my not so short talk. So we have some other functionality in BlueR. There are RFCOM sockets, which are virtual serial ports. They are very similar to L2 cap sockets, so I'm not going to demonstrate that. And you can also do some authorization and access control, like pairing, pin exchange, and so on. You know all this stuff your mobile phone is asking you when you want to pair a Bluetooth device. So you can all do this from within the Rust. And we also have this package called BlueR Tools, which is actually a binary package, not a library, but you can install it using cargo install. And it's providing some nice utilities, mostly for debugging your application when you're using BlueR. So you can exercise some get characteristics and directly talk to L2 cap and RFCOM sockets. Or you can use BlueMon to monitor Bluetooth devices around you. So let me zoom out a bit. So as you see here, it's like just scanning in this room what it sees. And actually, BlueR has an integrated database of manufacturers, so it can resolve the MAC address and the advertisement information to find out who manufactures the device. And what you see here on the right is the device name if it's advertised. Now, final demo, perhaps something more useful. If usually you use Wi-Fi, but perhaps in the field, like me, I'm doing some stuff with Raspberry Pis, which I also have at some clients, and they are not connected to the network. Sometimes you want to connect to a device over SSH, but if it's not in a Wi-Fi, it's quite difficult. So you can use the L2CAP protocol for that, as we know now. And using the L2CAT tool, you can tunnel TCP connections over L2CAP, completely in user space. You just need to run this command on the server. And then if someone connects to port 240, it would span bash and redirect the output of bash over L2CAP. And you can use this client command to connect to this port 240 and then interact with bash running on the remote host. Let's see if this works. So I have this command here, so I have to type it now. It's only a Raspberry Pi, so don't try to hack it. There's nothing interesting on it. And as you see here, I'm now in my left terminal, I'm also on a Raspberry Pi. And now to demonstrate that I'm not cheating, I'm going to disable my Wi-Fi.
Then you're not streaming.
But no, I'm not streaming anyway because... And as you can see here, I'm still connected on the Raspberry Pi. Okay, I have to type reset to reset the terminal. But I can even play a game of NetHack. Over Bluetooth. And that concludes my talk. So we have some things that are not implemented, mostly legacy stuff, but if something that you need is missing, don't hesitate to implement it and send me a pull request. So this is my summary. I think I don't have to repeat it. The talk was long enough. Thank you for listening. And if you have any questions, feel free.
Thank you very much. Are there any questions?
Yeah. Yep. Yep. So this thermometer, this temperature GATT protocol, is there any scaling allowed, or is it always 1 bit per degree?
I don't actually know. This is like part of the Bluetooth specification.
Okay.
And I think because you can change the unit, I mean, you can change the descriptor, you could use any scale you want.
So it's a freeform unit then.
It's like a self-describing.
Okay. It's not
maybe
actually just Celsius. Or...
If you use Celsius, like from the standard,
yeah,
then you have to look in the standard and see what kind of increment they're using.
Mm-hmm.
But of course, you could define your own unit and then you're free to do what you want. But then, of course, you're not interoperable with other devices that just want to read your thermometer.
Mm-hmm.
I looked into the GATT specification a while back, and I think it specifies 3: Kelvin, Celsius, and Fahrenheit.
Okay. Thank you. I didn't know that.
From memory, don't believe me.
I don't actually have a Bluetooth thermometer. It's just simulated on my my device. Any other questions?
Do we have to get the microphone there?
You told about your background in physics, and then how you went to doing your simulations, like a programmer. But something we're missing. Like, how did you get to know so much about Bluetooth? It's quite unusual knowledge.
Yeah, it was actually a project for a client, and we were required to do something with Bluetooth. And I was so much into Rust that I wanted to do it with Rust, but all the libraries were lacking some features I needed. So I, just started reading the source code and the specification of the Bluetooth daemon, and then just re-implementing the stuff in Rust. But then to understand it, you actually have to read a bit of the specification so you know what you're doing. So it was just by I was just forced to learn it, basically. It's no other way to describe it.
Yeah, I was thinking it would take a lot of time to read that kind of stuff. The code is usually not that well documented or well structured, and the specifications tend to be very long.
Yeah, it's true. But I mean, the Bluetooth daemon is quite easy to understand because you can just set a breakpoint in the Bluetooth daemon and see what is happening when you do some dbus code, and then you go step by step to it using GEB. That's why I did, to understand why my code was not working. And for kernel code, it was just patching the kernel and inserting some kprintf codes to see what is happening. I think this is the best method to understand code that you actually don't understand.
So you make a kernel print stuff.
Yeah, it's not that difficult. It's like people are always afraid of the kernel, but it's like normal C code, and if you can program in C.
Yeah, well, the normal programmer doesn't program in C these days. That's why there's kernel developers are seeking Rust developers these days.
Yeah, definitely, you are right. But I think there's a difference between actually programming and okay. The good thing about C is that it's very easy to understand. I think writing C code is quite difficult because it's very low level and you have to do lots of things manually. But reading C code is very simple because you only have like, I don't know, 5 or 6 instructions you need to know, and that's it.
I think we can defer this discussion.
So anything else?
So you said that
Keep going.
So you said that your library is a rewrite of the original library Blue R.
Blurts, yes.
Yeah, and so your library is on feature parity with with the old library.
The old library is not being developed anymore. It's like abandoned. So, and actually, I don't think there's any code left because it was not async, and I switched it to async, so I basically had to rewrite everything. But I mean, it's still in the Git history, so you can run git blame if you're interested and see if there are still some parts left over.
And does this library work with other async runtime like STDs?
Actually, I don't think so because we are using Tokyo Span to span some background tasks. So you need to have some Tokyo executor running.
Okay.
Cool. Thank you.
Yeah, thank you.
I'd say we do a short break of maybe 5 minutes so everybody can replenish their beverage of choice and grab another slice of the sheer amount of pizza, the mountains of pizza that are still left. And we will reconvene in 5 minutes.
this talk is about how amazing Rust is. So not about a specific project I did, just about the language Rust that we all love. Or maybe after the talk, especially if you're a Rust beginner, maybe hate Rust. But what you will see are the reasons why I actually love Rust. Because in Rust, everything is an expression. It's an expression-based language. And you can do so much crazy stuff with those expressions and combining expressions into big blocks of code that are still just one expression for the Rust compiler. I haven't introduced myself. I'm Philip, team lead of Clippy. Yeah, and let's start. So I didn't come up with any of those weird expressions. They're stolen from this test file in the Rust compiler called weird expressions. And yeah, you can run git blame on it to find the original authors of those. And I will just explain what's going on in those expressions and why Rust is so great. We can make this talk interactive a little bit. 2 rules: if you think you know the answer, just shout it out. But if you know that you know the answer, don't spoil it for the others. So let's start with the first exam, which is my personal favorite by Mara. Can you all read it also in the back? Yeah. So what's going on here? Who thinks that this code will compile? Show of hands. One person only thinks it will compile, or was it too quick? Yeah, give it another look. Okay, this is not a test that you can fail, so just show of hands. Who thinks it will compile? Go with your gut feeling. Okay, half of you. Okay, so who thinks this code will panic? There's an unreachable, below there's an assert, which takes an X of an array of a full range, compares it with a closure of sum 4. So who thinks this code will panic? Show of hands. Okay, spoiler, no code. All the code in this talk will compile, and it will also pass and not panic. So what is going on here? So we have a closure at first, and then we call this closure with a full range. Because we take an unspecified type and without a name, we can pass in anything we want. That will define the type of the closure, so we pass in a full range. That works, and then we do this. The match here is not a match to a closure, but it is a wildcard match, because this one is a match to a wildcard. It's not the syntax for a closure. So this matches here and will return underscore, will return a closure to sum 3 and will assign it to X. Not to that X, but to this X. Because this, again, is a pattern which takes X, or X as a variable binding, and then X has the closure assignment to this. And this matches is true because it uses the same trick as this one. This is not a closure. This is a pattern that matches to a wildcard. Maybe if we use Rust format, all of this will become clear, because Rust format removed those initial pipes. So now you see this is a wildcard match. This code is unreachable. This is also the reason why we have this unused here. And this uses the same trick, but Rust format can't format it because it's in a macro. It matches to a wildcard, so matches return true. Doesn't matter what we pass here. And assert is successful. And this is why Rust is awesome, because we can do this. And why does this work? Because a pattern in a match statement or something, the grammar for the pattern is you can start a pattern with an OR. And if, what was that? Oh, okay, I can't touch the adapter. Yeah. And if you want to know such details about Rust. There's the Rust reference, and it specifies this at the top. It's or question mark means this or can be there, or you can leave it out. And most of the time, you just leave it out. Yes, so that was the first example. Rust has great error messages, and if you want, you can also write your own error messages with the macro compile error. If we run this code or try to compile it, we get an error with your text here. That's not about really expressions. I just found out that this macro exists and I found it cool. So, next example: zombie Jesus. That's interesting. So this is possible in Rust. I mean, what type does a while loop take in the condition? A Boolean. But it takes a return. But what type has return? Who knows what type return has? No? Yes? The explanation. Yes, it's a never type, not a unit type. And never type has the never type unifies to all the types. So never type can be inferred to be Boolean if it needs to be Boolean. And so in this case, return becomes a Boolean expression. Here it becomes a Boolean expression, and so on. Here it's just a return. Probably here in this case, it is a unit type because our function returns unit. So yeah, there we go. And yeah, also quick example. Not much code is executed here because it will return in the while loop. And we see that if we add some print statements, it will only print 0 and then it will return in the while loop. So no infinite loop here. Maybe you're not really familiar with the never type because it's not stable. And there's a reason for that, because the never type, if the Rust compiler can't infer what type the never type should be, for example, in while block, it's easy, never type should be bool. But in some cases, Rust cannot infer the type of the never type. For example, this, we have a closure, we pass the closure to something that is completely generic in the type with no restrictions. And then if we run this, the compiler will say, okay, if I don't know what type the never type is, I just say it's the unit type. And this is the reason why the never type can't be stabilized. And if you want to know details, you can read this post. That explains it in detail. It's pretty complicated in an edge case of C code that is bound with FFI to Rust. I can't explain it, it's too complicated, but I will send out the slides afterwards and you can read through it if you want. This is also great. Maybe you saw this already. This is valid Rust code. Union, 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 union. Did I miss something? Yeah. And it builds, and it would also run, but it would just do nothing because there's no main function. Rust will complain if we remove this because we have names that are not camel case and code is unused. But this is all valid Rust. You can't do anything with it because you can't construct it, because it's a union that takes itself as a union. And yeah, you have to start somewhere, but you can't construct it. So that's that. So you can't do anything with it, but it's possible. You can just write union 9 times and you have a valid Rust program. And this is possible because in Rust, other than other programming languages that we don't want to name here, you don't have to write struct dog to say that dog is a type in this case and a name in another case. You can just write dog in Rust, and if dog is a type, then if it's expected to be a type, then it will look up in the type symbol name table and take that name. And if it's expected to be identifier, it will look into another symbol table. So the namespace of types and namespace of symbols is completely separate, and there's no confusion in the Rust syntax what is what. And that's why you don't need such struct dog to say this is a type and then dog to say this is a name. You don't need any of that. And union, in Rust you can't do this with keywords because like struct is a keyword and you can't name something struct. You can do it with r hashtag struct if you want to name something struct, but you can't do it usually. But there are weak keywords, and union is one of them. You can just use them in your code. I don't know the history why union is a weak keyword and not a strong keyword, but probably because you almost never use unions, and union is a general word. So yes. Yeah, type of assignments. So this is valid Rust code. So you can assign x to 0 and x to 0 and then compare it. What will be the result of that? Yes. And now, in this case, you can add 0 to x. X is still 0, we assign it again. And then you can set x to 1. And what will be the result of this comparison?
True,
Yes, why is it true?
because it's unit equals unit.
Yes, exactly.
That's my guess.
Yes. Assignment in Rust is an expression, and we can also verify this. Here, x is 1 because we assign it to 1 here. And set is false because union is not smaller than union, but all the other things are true because an assignment in Rust is just an expression, and the assignment expression has the return type unit. Has a return type unit. And if you compare any unit value with any unit value, it's true. The same works with swap. Swap returns unit, and unit equals unit is true. And yeah, this again leads to that this is valid Rust, but it doesn't do like maybe for other inferior programming languages do, and assign y to 5 and x to 5, 5 to x and 5 to y, but it will actually assign, give y the value 5, and then x will be union. You may think, wait, isn't Rust perfect? This is the problem, right? No, it is not a problem because Rust is strongly typed, and if you would use x as an integer later, you would just get a type error and everything is good. So Rust is perfect, and we can move on. This is another great one. What will this print? So the name of this is buffer install because obvious. Who thinks this will print 1? No one. Who thinks this will print 3? Few. Who thinks this will print 42? No, that would be a coincidence. And who thinks this will print 13? Because it will print 13. Because this is a wildcard match, wildcard match, wildcard match, and then you match two wildcard, but only if 1 plus I plus 1 and I plus 1 is not equal. But we just saw assignments and also add assign is unit type, so it is equal. So it will always evaluate to false. But each time you evaluate this, so here you add 2, here you add 2, then you evaluate it again and add 2 again, and so on. And you do this 6 times. 6 times 2 is 12. Use with 1, so 1 plus 12 is 13. So obviously it will return 13. Rust is great. Okay, one more example. This is completely useless, but it's funny. Punch card. I mean, this is literally, the main function is literally the only thing you can do with this. You can print it, debug print it, and it's, yeah, this. Yeah, I mean, it's really useless. But what we can learn from this is the range type in Rust, the start and end index of range have absolutely no restrictions. You can use any type for this. So this is also why you can use a range as the end type of a range. And then of that range, you can use another range as the end type of the range, and the start type could also be a range. It could be also anything. In the end, the type you build with that, you can't do anything with it because all the traits the range implements has some type bounds, like must be partial OR, and index must be partial OR, or if you have clone, then don't think clone has a restriction. But yeah, all the double-ended iterator has some restriction. A must implement step, and yeah, so you can't do anything. Debug printing also doesn't have any restriction except that it must implement debug, and range implements debug. So a range of range of range of range still implements debug, so you can print it. And that's it. You can also clone it, but and it wouldn't be talked by me if I wouldn't include something with Clippy. The Clippy dump attribute you can attach to any expression, and if you then run Clippy on it, it will print on standard out how Rust sees your code in high-level intermediate representation, and we see this expression is a struct of a range, and the end field of the struct is again just an expression, of course, because everything is an expression, and the expression is then again a struct range, which has a field, which is again an expression, and this goes on and on and on and on and on. Yeah. Clippy dump works with every expression. If you're interested how Rust sees your code, then you can just attach this to your expression, and that's it. And that was my talk, and this is why Rust is awesome and why you should love Rust and never write code like this. Any questions? So that's some more.
Should I take the mic?
I'll just come on.
So, controversial question.
Yeah.
So, for you to get started, although this makes Rust amazing language and very expressive because
Yes.
it has expressions, would you think or elaborate that it maybe make it less accessible for the wider audience?
It definitely takes time to get used. It definitely takes time to get used to this expression style, because there are not many languages that come that implement this expression style where you can just chain everything together and then you still get valid code. So yes, it is a higher burden of entrance, or can be, but I think if you get used to it, I think you start to love it. That you can chain those expressions together and you still have an expression, and it still works. It's still Rust, and it just scales, in my opinion. Okay, any other questions? Yes.
Yeah, it's not a question, it's just a comment. I mean, it's an answer to your question. I mean, you could just compare what he did to what people do with the CPU processor, and then ask what is worse.
Right, but it also makes it less accessible.
Yes, I mean, to be fair, no one writes code like this. Some of this stuff comes out of a fuzzer that just fuzzes the Rust grammar and spits out some weird expressions that are possible in Rust and made the Rust compiler ice. Ice means panic. And then they included it in a nice way in this weird expression example. So this is not, some part of those expressions are not human written. It's just some fuzzer that came up with this example and then they included it as a regression test. And some stuff is just fun. And you would never write code like this, but you can. And yeah, there's an argument for it. Makes it less accessible, but I'm on the side. If everything is an expression and I know this, then I can use it.
This union type declaration, have you ever seen this anywhere? I've never heard of this before, and I've been in Rust for years.
Union itself?
Yeah.
Yeah, union in Rust is just like union in C. But if you want to do something with it, then you have to put it in unsafe code. Pretty much all operations.
Automatic discriminator.
No. So it's using a union is pretty much completely unsafe in Rust.
It's like an FFI compatible thing.
Yeah. I think it's mostly for that, because in Rust you don't really need a union because you have really powerful enums.
It's when you get a value from an FFI function, but in C, obviously, there are crazy types. This is how you represent crazy types.
Yeah.
Not like this, but with unions. Yeah. So union is a keyword. It's like struct. So when you can write struct X, you can also write union X. So you can write something like this. Oh, yeah. That should build now, hopefully. Yeah, so union is just like a struct, just as a union, and union works like in C, and also has the same undefined behavior things C does. Okay, any more questions?
Yeah. How does that punch card actually work, considering associativity precedence? The range actually has one restriction: the start and the end must be the same type. I would expect it to like either like everything would come at the beginning of the range, everything would come at the end of the range, and the types would be unbound, so it wouldn't work.
I haven't thought about this. Where do we have it? Yeah.
At the same time.
So the clip you done showed that only the end of all the ranges is set.
This is for you have to start it with an those are open ranges. So all the ranges here are open on one side, right? So
have you tried this in Rust Analyzer?
Rust Analyzer.
Yeah. Does it work? Does it break?
I don't think so. I mean, all the tools work on it. Well, formatting. I mean, those are open ranges, and open ranges don't have a start and end index. And if you have half open ranges, you only have an end. And I guess if you combine, and then you don't have this restriction that start and end must be the same. I guess here.
I think it's all half open ranges except the last one.
This one. This is a full open range. No, it's half open.
No, the last one should be fully open, and the end parameter of the range before. So
yeah, something like that. Yeah, I think it's just half open ranges, and they only have an end or a start, and that's why it works. For example, if you put something here, it won't compile anymore. Like you get a mismatch type. Expected integer found, range 2 inclusive, range 2. Yeah. Rust has great error messages. Another reason why you should love Rust. Arguments to this function are incorrect. Thanks. Yeah.
The kind of error messages I got every day before Rust had the inbuilt ranked functionality.
Can you run a Rust format on this one?
Yes, it does nothing.
Oh.
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 Yeah.
If you change your function to return unit, it should print the type mismatch.
Sure, why not?
Yes.
Yeah, expected unit got range 2 inclusive, range 2 inclusive. Yeah, it's also always range 2, so only an end index. Yeah. Yep. Yeah, one Easter egg in Rust, maybe you notice. Let's try to break Rust. Because if you want to see the Rust compiler panic, then try to break Rust. And we get an internal compiler error. Yeah, but remember, the compiler expectedly panicked. This is a feature. Okay, I think we're done. Thanks for listening. Have a great evening.
All right, that's it for tonight. Grab another beer, have some conversation in the next 40 minutes before we have to leave the premises, and enjoy. Thank you for joining us.